TV from other dimensions has a somewhat looser feel to it.
Yeah, it's got an almost improvisational tone.
I switched it over as they went to the thing right there. How's everyone doing? I'm here for just a moment. Let me hop over to the thing. Okay, what questions do people have? We could talk about decision trees, knowing how to read the leaves or whatever. We could talk about probability. I think the project's a great review on decision trees. When you think about your leaf numbers, it really helps. I'm just kind of drawing out an example decision tree. Knowing how to read it is the big stuff right there. We could talk about probabilities. There's a few things that I always think you should know. Like we did this in our class. If you're watching this right now, I'll look at the questions here in a second. We did where we talked about the rules of probability, and I think we need 4 boxes here. We have the rule, which is like the addition or the multiplication, and then we have the sign of it, which is addition or multiplication. Then we have the I guess what must need to be satisfied condition, which the addition is going to be disjoint, and multiplication, if you're saying it right now, you're on track, is independent, and that's horrible handwriting. It needs to be updated. Well, it's on the practice test. If we go here, so we should be able to see, let me pull this down from up here. So you'll see it in the practice guide stuff right here. So let's go here to the practice material right here. Let's bring this down right here. It is located, there's the current review right there. Here's decision trees. We should be seeing this right here. So there's decision trees right there, and it's also on the syllabus. Sorry if there's any confusion on that. It's in the part right here, and also, where's my mouse go? And also there's this question on it appended right here on the list. So these have been on the list right here. It's on the syllabus. Sorry if there was any confusion right there. I saw someone in the chat saying, well, where is it? So there are right there. I saw some more questions in the chat. How do you know the shape of the sampling distribution? I see a lot of questions. Can we go over decision trees? I think people want to see decision trees. We just haven't been doing that lately, so I was like, that's a good one to do, and those are on there. So please be reviewing those, and they were on the projects. Those are very important, and the test doesn't have it, the practice test doesn't have it, but it's been here on the list. So this right here is the version of it, which is on the review material page. So this is on the review material page. It just moves around from test 1 to test 2, and if you notice the way we're plotting it out right here, but make sure you know how to read decision trees. That is very key right there, Keaton. So make sure you know how to read these, and it's on this test. It just got moved about, and it's been on the syllabus. So sorry if there's any confusion about that. You will be asked about decision trees, and people are wanting to do some decision trees questions. So let's do a decision tree to start. Let's hop in here and talk decision trees. Let's open up the data. And then we see some shapes of distribution stuff. So let's bring up the data bigger. Is the equation sheet on the practice sheet going to be the same as tonight's? That is true. And I see some questions. Everyone's saying decision trees. Let's do decision trees. So let's go right here and go in and change to decision trees. So, hey, Grant. Oh, nice job, Adriana, answering some questions. So we're gonna make a simple decision tree right here to predict. Let's go over here and predict if somebody has broken a bone. So we're gonna predict if somebody has broken a bone. We're gonna drop these into here. And when you think about a decision tree can take categorical X's, categorical Y's, and it can use them however. So a decision tree uses, if you look at these red ones, what do these red things represent in jump? What are the red things in jump right here? The red things in jump are what? The red things in jump are what? What do the red things represent? What do the blue things represent? What are the red and the blue in jump? We got red, we got blue. What are these things? What do these variables represent when they're red and they're blue? I see no one saying in the chat. So, let's see. No one said it yet. Red means categorical. Red is categorical. Adriana, you're right. Red is categorical and blue is quantitative. So you may not realize it, but you're seeing some of the concepts here. That decision trees can do a categorical X or quantitative X, quantitative X, quantitative Y. We can put these any which way we want to make our decision tree. So just doing two different decision trees right here, we can get very, very different decision trees. We'll just predict gender up here, and we'll drop this into here, and now we have two different decision trees. Now the points are being colored by gender, so we have two different types of trees right here. We have a quantitative tree and a categorical tree, but this kind of highlights the point that decision trees can do a quantitative X, quantitative Y, categorical X, quantitative, anything quantitative, categorical. What do decision trees not use? I want to see it in the chat. What variables do decision trees not use? Decision trees don't use what? What do decision trees not use? Identifiers, you are right, or things that act like identifiers. That is the only thing decision trees do not use. So how do we read a decision tree? Well, let's look at some of the output. We're going to go split, split, split. And no, I got a non-symmetric tree. So let's prune below just for making it look like a nice tree. And let's look at this tree. So what we're trying to explain right here, so we're trying to explain if somebody is male or female. So when you look at this right here, which of these groups is most likely to be male? Group 1, 2, 3, or 4? And I'll highlight it even better. Group 1, Group 2, Group 3, or Group 4 is most likely to be male. Which one is most likely to be male? And they're saying in the chat, they're saying 1 is most likely to be male. 1 is most likely to be male, which is right over here, this leaf right here. Now when you look down at this, what do we notice? This is leaf 1, this is leaf 2, this is leaf 3, this is leaf 4. And you know what? If we do a little trick right here, I think we can get it all on one screen. So here's what I would do, and this is big suggestions for the test. And I love that we have the annotate ability now. Where'd my snipping tool go? So let's take a snip of this right here and pretend we're doing it on the test. Okay, so we hop back over here to rules of probability, and now we zoom out. Okay, so when you get your test, what you need to remember, what the heck is a Roth IRA? That's a good question. Roth IRA is a savings account. Roth IRA is a savings account. We get here leaf 1, leaf 2, leaf 3, and leaf 4. That is super hard to see. That is so hard to see. Can I do it? Maybe black will be really good. 1, that's good. 2, 3, 4. So does everyone see that right there? 1, 2, 3, and 4. Now when you get down to here, the bottom leaves are your final leaves. So we go down to the bottom here and we go 1, 2, 3, 4. For many people who worked with me in Stat Lab, we would always identify these leaves right here to say, okay, that's the first, that's the second, that's the third, that's the fourth, and these are the leaves in the order they appear. Oh, thank you, Jordan. You're awesome, Jordan. Maybe, I think are you a former student? So good to see you then. Good to see former students in here saying hey and wishing people good luck. We appreciate the positive energy. That is awesome. Continuing on down here, we'll go to leaf report. And let's do this. Let's grab the leaf report and see what we get right here. The leaf report is also telling us information about this tree. So in the leaf report, we take our leaf report and what do we put? 1, 2, 3, 4. 1, 2, 3, 4. Does everyone see how we are connecting? I'm blocking it off a little bit now. Does everyone see how we are connecting the leaves right here? These are the leaves, 1, 2, 3, 4 leaves, with the leaves up above. Now let's scroll back up and remember, which of these was most likely to be male? You were saying it earlier. Which of these leaves is most likely to be male? Leaf what is most likely to be male? What leaf is most likely to be male? If you look, these are the people up here, which are male, and these are the people down here, which are female. Now the probability of it changes as you go through. Like right here, the probability is about 50-50, as it is in that middle leaf also. You can kind of look at these. You know what's really interesting? You may not have ever noticed this, but what I'm drawing right here with these bars is actually what you get when you go down and look at this right here. What I'm highlighting right there is the same thing as this, and they're saying it in the chat, they're saying first. That kind of ratio of male to female in that first leaf is the most likely to be male leaf. And so if we were to describe the characteristics of someone who's most likely to be male, sorry males, but apparently we are likely to have a GPA, let's follow it over this way, that is less than 3.72, and we apparently we either have a Roth IRA or do not know what a Roth or do not have a Roth IRA. The responses we gave, which more likely to be male responses, were lower GPA, less than 3.72, and when we were asked about a Roth IRA, we said we either have one or don't have one. Now, who is most likely to be female? Most likely to be female is leaf number what? Most likely to be female is leaf number what? Look at the information given to you, is leaf number 4. If you notice, females are the red dots and males are the blue dots. The female leaf that is most likely female is leaf 4 right there. So now we scroll down that we've marked up our sheet and we can go right here and talk about who's likely to be female. Someone who's likely to be female has the GPA that is greater than or equal to 3.72, and also this individual responded with that they do not know what a Roth IRA is. So this is what, and it's interesting, so you would think if someone has a high GPA and they don't know what a Roth IRA is, the probability of them being female is very large, and let's go and look at that. In leaf 4, the probability of being female was, what was it? What was the probability of being female in leaf number 4? The probability of being female in leaf number 4 was what? Do you see leaf 4? Do you see the probability of being female in leaf 4? The probability of being female in leaf 4 was, I might be saying it in a moment, 74%, you got it, it's right here. That's the probability of being female in leaf 4. And it's actually interesting because the male probability in leaf 1 was that. And what you are viewing right here, this 74% is right here. This mark right here should be about 74% female. Where this mark right here, they're both about 74%, is about 74% male. So if you notice, the blue right there is about 74% male, and the red right there is about 74% female. Now the decimals are more exact down below, but those percentages, kind of link the graphics and be like, okay, that's showing me the percentages right there. It's showing me the ratio of males to females, which is what I'm actually seeing up here at the top. Like, connect all your graphics. This right here, wow, look at that. That's almost exactly 74% male because the male goes that way, and then this one is almost exactly 74% female. That's what you're seeing up there also. We're just trying to make sure you know how to look at these graphics. You know what you're seeing. Has anyone had like an epiphany moment and be like, oh, that's where everything's connecting? And that's what I hope to give you right now. I'll be like, I see it now. I see what this output is showing me. I see how to follow through the tree. Just kind of a quick review for those. You know, this is a quick review because we've done this concept a lot. We've done a lot of decision trees and just want to help you follow through on those. What additional questions do you have basically being able to read this output? The bottom portion just gets you the amount of people in each leaf. I had that moment on the project, Caleb, that's awesome. Can you explain when to use large enough N? Let's do that. Let's do conditions. Decision trees, now conditions. Condition 1, I want to see it in the chat. I don't want to hear any QQ straight enough, no outliers, plot doesn't thicken. Condition 1, what is condition? I don't know what condition 1 is. And we're just doing some quick review today. Randomness, that means we randomly select. I'm not going to write it because I can't write. If I have to scribble some numbers, I'm good. If I have to write longer things, then. Condition 1 is randomness. So condition 1, there are no orders, but you'll see why I do this. Did we take a random sample? Condition 2, what's condition 2? We could be specific. Really? Okay, I won't do it now. There. Did we sample less than 10% of the population? Let's talk about how these two conditions are met. One, we like to do for the random condition, we like to explicitly state something as random. It's the easiest way to know it's random because you can kind of debate it like, is it random? Is it not random? We can have it where it doesn't pass a condition. We've done that. I mean, I will say this, and this goes for a third test, which I haven't seen, it does not exist yet. We do like to have them pass conditions. With that said, you can fail conditions. Do not think that just because we're doing a test that we'll always have it pass. A lot of times we'll say like, even if you fail the conditions, continue on. So condition 1 is random, which in the problem, we like to state explicitly that we did take a random sample. Condition 2 is less than 10%. Now, how is this met? Here is a question for you. We went out and want to understand UT students. we took 10,000 UT students. Do we meet the less than 10% condition? 10,000 random UT students. Do we meet the less than 10% condition? Do we meet it or not? 10,000. How would you answer that on the test? And you might be free to ask us something. We took 10,000 UT students. No. What would you say? You'd say, no, we do not meet the less than 10% condition because. And Caleb's right, if we don't meet these, the normal distribution can't be used. It does not pass, and I'll give the answer, you might be typing in chat, but if it was on the test, I would write, no, 10,000 students is more than 10% of all UT students. And that's assuming we don't have 100,000 students. What if we took a sample of 200 students? Then you would say, yes, we passed the less than 10% condition because 200 students is less than 10% of all UT students. Because there's not, exactly, Jenna, you are right, there's not 100,000 students, so we cannot say we pass it. Let's make 2 more mods in here. Caleb, you are now a mod. Jenna, you are also going to be a mod right here. Thank you. Amazing job moderating yesterday when I was teaching. I really appreciate it. Thank you for everyone who's modding. Now, we get to the conditions everyone gets confused on. Let's make this very clear. We're going to put right here in red. We're going to go condition 3. And this will be success, failure, condition. The success, failure condition is we have at least 10 successes and 10 failures. I'm going to put something right below it right here. We're going to put sampling distribution of sample proportion, and we have NP, comma, NQ. I'm going to go right off the screen. Darn. And then we have here, let's get this all on the same screen. There we go. And then we have confidence interval. I have to move my arm. Confidence interval. Good. For the true proportion. Good. And I missed the R, which I was missing all yesterday. And you know what we can do? We can go all fancy on this. NP hat and Q hat. So let's insert equation for the moment. And we're going to throw a little hat on this one because we can. We're in Word. I could have just drawn it too. That would probably been quicker. NP hat, and then we go here N, and we put in Q hat. We're going to copy paste this P hat. Does everyone see the key word on how you know it's success failure of some form? How in the world did I know it's success failure? How did I know it's success failure? How did I know? What is the key thing Brian is trying to proportions? Brian is trying to illustrate, there's no pause condition. You just pause, you stop and think. So with this right here, proportions is we need at least 10 successes and 10 failures. Now I want you to think about something interesting. If you're making a confidence interval for the true proportion, you would not know P. So since you don't know P, then you could not possibly use P down here if you don't know P. Does that make more sense to people that the third condition when we do proportions is either NP, NQ for the sampling distribution of the sample proportion, or it is NP hat, NQ hat when we make a confidence interval for the true proportion because we would only have P hat. When you make a confidence interval, you don't know P because you want to know the true proportion. But when you're making a sampling distribution of the sample proportion, you actually know P. If you look at the equations, the mean is going to be P. So that's kind of a review right there. Please ask questions if you have it. I know I'm just hitting you with so many things right now, like the big questions people ask, like when is condition 3 success failure, and when is it large enough N? So let's go down here and let's change colors to now, we're going to go to blue, and condition 3 is going to be large enough N. And the sample size for the distribution of the sample mean is large enough that it will be nearly normal. Now let's do some things right here. First, check your shape. check the rule for the shape. Check to see if you meet it. These are the steps right here to do it. These are the steps. Between true and sample proportion is Madeline. We'll do that next right here. Great question. Remind me if I am going quickly and I want to do that one next. So right here we have check your shape, check the rule, and all this good stuff. Here are the shapes we generally use. The shapes are 1, it can be normal, and that means the rule is 1. 2, it can be skewed, and that makes the rule 30 or 25. There's nuance to why there's not an exact number, because what is skewed? Well, what if it's heavily skewed? If it's heavily skewed, then we would have a sample size of at least 100. But what are you noticing about the more skewed I make this? Let's make this one only look skewed, normal skewed a little bit. What do you notice about the more skewed I make it? The more skewed I make it, the wider n needs to be. The more skewed it is, the wider n needs to be. The more skewed it is, the wider n needs to be. And we did this one yesterday a little bit because on a true-false question it said it was normal, and there you go, the bigger, the larger. That's why it's called large enough n, because the more skewed it is, the larger n needs to be. And it's not that this distribution will become normal, the distribution of the sample mean of size that will become normal. So we'll get a normal distribution, that should look normal. Let me undo that one because that looks still skewed. I want it to look pretty good normal. The distribution of the mean of sample size 100 will become more normal and tighter as n increases. So this right here, these will become more normal and tighter around the mean as n increases. So we're not talking about the observations are going to be normal, but the distribution of the means, and this is where we call it the central limit theorem. This is all the central limit theorem in practice right here, saying that the distribution of the sample mean will become more normal and tighter as n increases. So think about this. If it's really skewed, you need a larger n to make it more normal. And let's just see one last thing with this, because I think for anyone watching this, it can be really shown off to you right here. If we go to central limit theorem applet, I want you to tell me the shape of this original distribution. It looks very what? Looks very normal. So what I'm going to do is I'm going to take samples of sample size 5 and make a new distribution of all the means. So each of these is just a new sample of 5 and the mean from that. And I can repeat this over and over again and build up a distribution, and the new distribution will be more normal and tighter. But look, this was normal, so this is also normal. Now this one is not heavily skewed, but it's kind of skewed. So 25 is kind of large enough. What the new distribution is here is not a single observation. The new distribution right here is the sampling distribution of the sample mean of sample size 25. So when you see me doing this right here, all of these blue dots are the average of 25 individual dots. And what we notice right here when we build this distribution, the new distribution down here is tighter and more normal. Now this might still have a little bit of a skew, so we might need a larger n, but the more skewed it is, the larger n needs to be. Tell me, is this distribution right here, let's do this, is this distribution right here heavily skewed or just a little bit skewed? Heavily or just a little bit skewed? Only a little bit. So with this right here, when we do the average of 25 and we keep making this, now we would see the bins are too small. The way it's drawing it, we'll draw this out right here, sorry. Since the bins are so small, it looks weird, and it will make it more normal and tighter. So sometimes the bins get so small that I can't really draw it well, but you'll notice as we increase n, it just gets tighter and more normal by a factor. It's just with the bin width being so tight like that, it can't draw the bars properly. And I see a lot of questions in the chat, but does that help everyone understand a little bit better this condition right here, that as we increase n, the distribution will become tighter and more normal? And when is n large enough? Do we use large enough n when it is quantitative? That is correct. And success failure when it is categorical. Jenna, great answer right there. I haven't gotten over number 6 on the practice exam. We might not have time for that right now. Do you have any tips for memorizing the sampling methods like rhymes? I don't, Isabel. We should come up with some of those. Great question. The true proportion is the theoretical correct proportion of the whole population where the sample size 1 is what we actually observe, I believe. The true proportion is what we would expect, Caleb. We would expect to see the true proportion in a sample. So it's theoretical. It's saying if you took a sample, here's what you would expect to see in a sample. You'd expect to see the truth, such as the mean of the distribution of the sample mean is also the true mean. Last two questions, I think Madeline had one too. Can you explain what the difference is between the true and the sample proportion is? We got that one right here. The difference between the true and the sample proportion. I'm going to try to do rapid fire some questions here. P is true proportion. P hat is sample proportion. P is true proportion, P hat is sample proportion. And with this right here, how does a true proportion read? One of the questions on the practice test says something like 25% of water heaters will last at least 10 years. So that's telling you that's the truth. So when it says 25% of water heaters will last at least 10 years, that would be P. But later on in the question, it says something like 16 out of 50 water heaters lasted 10 years. Now, when you hear 16 out of 50, what do you notice? 16 is X, and N is 50. And X over N equals P hat. So what do we get right here? We get that 16 over 50, and we get 32%. Or it can be displayed, don't worry about decimals or percentages, but P hat always comes from a sample size. So if it says something like 25% of water heaters will last at least 10 years, that is P, because that's just telling you the truth. Like a company advertises this, we're claiming that's the truth, so apparently they know we're saying that the truth is 25% of water heaters last 10 years. But then in a sample of 50, 16 lasted out of 50, 10 years. Is there another review besides the one we did in class? Sometimes people have additional review sheets. I try to get those and pass them out to everybody. I try to post them too, but we've got all the reviews we've been doing. Can you go over how to do probability when it says at least one? Okay, let's do one of those. Remember, you can come back and review this video. That's the difference between the true proportion and the sample proportion, and we want at least one problem. Okay, let's do this. So, there we go. Okay, I'm making some blank pages. So in at least one problem, these are tricky. Are you ready? Here we go. Remember, this is recorded, and I have to leave in like 9-10 minutes. So that's why I'm like rapid firing questions. Here's an at least one problem. Let's say we want to figure out the probability of winning at least one scratch-off ticket. So the probability of winning for a scratch-off ticket is going to be equal to 20%. What is the probability of losing on a scratch-off ticket? If the probability of losing on a scratch-off ticket is, the probability of winning is 20%, what is the probability of losing? 80%. You got it. Now this is the way I like to draw out my at least ones if I go into depth on them. I'm going to buy 3 scratch-off tickets, and I want to know that I win on at least one. Did everyone hear that? Brian is buying 3 scratch-off tickets, and he wants to see that he wins on at least one scratch-off ticket. So let's give this a shot. Well, what could happen? Brian could win on 0, 1, 2, or 3. So this is what could happen. Now what I want to see is let's use some nice blue marker on that. I want to see this, but I don't want to see this. Does that make sense? 0 represents, and I think they figured it out in the chat, great job. If you knew it like that, you are on track. So I don't want to see that I lose on all the scratch-off tickets. That's what the 0 represents, because I can either win on 0, 1, 2, or 3. So now we need to figure out what this all means. Well, think about this. What we have right here is the probability of winning on 0 and the probability of winning on, or I should say or the probability of winning on 1 or more. Do you see how I've just rewritten these probabilities as the probability of 0 and the probability of 1 or more? Does that make sense right there? Is everyone following me right now? And I want you to think about this. Will there be a problem asking me to leave? Oh, no, Sydney, no worries about that. Those require permutations. They're better done with applets and stuff, but this right here is we won't do at least 2 or 3. No, we won't do that. Don't worry about it. So this one right here, we have that Brian wins on 0 or he wins on at least 1. What is the sum of these probabilities equal to? What is the sum of these probabilities equal to? If I add together those, hint, one of those must occur. So what is the sum of those probabilities? If one of those must occur, the sum of those probabilities is equal to what? If one of those must occur, I must win on 0 or at least 1. And I can't do, they're disjoint probabilities because I can't win on 0 and 1 at the same time when I buy 3 scratch-off tickets. What is the sum of these probabilities? 1. Because I either have to win on 0 or at least 1. One of those things must occur. Now let's take a look. Because now all we do is algebra. Oops, I can't algebra. There we go. And we just do this. The probability of winning on at least 1, do you see it? It's basically not, and I want you to read this. The probability of winning on at least 1 is everything but losing on all your lottery tickets. So something happened other than you lost on all of them. Does that make sense? Let's look at this. Something other than losing on all your lottery tickets, that's that. And read it. When we look at 1, 1 is everything. Everything but losing on all your lottery tickets. Does that make sense? So I think Sydney found it. All we have to do now is find the probability of losing on all your lottery tickets. Because either you will lose on all your lottery tickets or you will win on at least 1. And that's where the probability came from, because all we need here is 1 minus 0.8 to the third power. And I can't do that one in my head. Oh, I'm trying to do it. My brain is breaking. So let's see who has it. It's 0.64 times 8 minus 1. So 0.8 times 0.8 times 0.8, that's there. And there we can see it now, 1 minus that. So it's 0.488. Not bad. Probability you win on at least 1 lottery ticket when you buy 3. Don't buy scratch-offs. This here is the probability. So this one has an associated probability. So the probability of this is 0.512, and the probability of this one is 0.488. Does that make sense right there? Why to the third instead of to the fourth? Good question. Because you lose on all 3. Think about this. You scratch your first and it's a loser. You scratch your second and it's a loser, and you scratch your third. I know there's 4 numbers up there, but the probability of losing on all 3 would be you lose on the first, you lose on the first, and you lose on the second, and you lose on the third. Now, here's a really important quickie question. Why am I able to multiply these probabilities? Why can I multiply all the probabilities of, like, you lose on the first, you lose on the second, and you lose on the third? Why can I multiply all 3 of those to find the probability of losing on 3 scratch-off tickets in a row? Because that's what I'm doing right here is I'm multiplying 0.8 3 times. I'm doing 0.8 times 0.8 times 0.8. What rule of probability allows me to multiply scratch-off tickets probabilities? Because they're independent. You are right, Jenna and Shelly. Nice job. Let's make Shelly a mod here too. Last quickie questions. I'm going to stay till like 2:03 and then we'll end the stream. Let me point out one big thing here. There were a few people asking about some of the questions on the practice test and stuff. So I want to point this out. There are videos going over everything right here. Well, that's the chapter review videos, but there are videos going over everything right here. All the different questions, if you scroll through the playlist. So I know I did the big review yesterday. It's good review. We did a lot of stuff in there. But if you're doing a practice test question, there are questions that go over everything on here. Decision trees is at the end, and probability, all the things right here. So you can see how to do each question on the practice test. Can you go over the probability rules really fast? Yes, I can. Sorry, if someone's like, man, he went so fast. I'm sorry. We're running out of time. I have to go teach. All right, here's our big box right here. You ready? So let's go 1, 2, there we go. Okay, so now let's call it, ooh, that's 1 too many. Spaced out too far out. Okay, let's try this again. I'm not going fast enough. I think that's okay. This is gonna be the name of it right here. Sorry for the bad handwriting, I have to do it really fast. This is the name of it. This is the sign of it. This is the condition. And this is the word. So we have the name. First name is going to be the addition rule. We'll just call it add for short. The sign is going to be sum. The rule is the condition is disjoint. We must have disjoint probabilities. And the word is or. The next one is multiplication. I'm just going to call it mult. And the sign for this is the multiplication sign, as is. The condition is independent. independent right there. Sorry for the quickness. And we're going to do and right here. The name for the last one is complement. Complement. And the sign is minus. There is really no condition for them. And, well, let's do this. We just do 1 minus the probability of A. And the word is not. I like to say not, like not the event. Does that make sense right there? We're running out of time. It's legible. I have the worst handwriting. But the name is the addition rule, the multiplication rule, or the complement. Those are all rules of probability. So that's just a quick review right there. What does independent mean? Independent means if you know one, it gives you no information about the other. So if two things are independent, let's say studying for the test and getting an A, are those independent or dependent? You know someone studied for the test. Does that tell you anything about them making an A? Not do you know they made an A, but does that give you information about someone making an A? Studying for the test, those are dependent events. So studying for the test or making an A depends on studying, but you wouldn't say you will make an A if you study. It's just that it changes the probability. So knowing someone studied for the test would change the probability of them making an A. So those are dependent events. How about our studying for the test and making an A disjoint events? How do we do that one? And these are the things we did yesterday. You have to ask yourself for disjoint, if one happens, can the other also happen? And if they can, they're not disjoint. So can you study for the test? Can you also make an A and study for the test? These are not disjoint because you can make an A and you can study. How about if your parents bring you to the pet store and they say you can only buy a cat or a dog? There's no way. So think about this. Buying a cat or a dog would be what if they say you can only buy one of the two? So you know someone bought a cat at the pet store. What do you know about them buying a dog? Well, they should buy a dog. If you know they bought a cat, those are disjoint because the other one can't happen. And just by virtue of the way I set it up by saying you can only get one pet. So if someone got a dog, you know they didn't get a cat. Or better yet, if they got a fox, they picked out a fox, they can't also get a dog. So they can only get one animal. So all the animals they get, if they can only get one, would be disjoint. Think about this, grades. Grades are disjoint because if you make an A on this test, you can't also make a B on this very same test. But there's so many different things here. Does that make sense on what disjoint? We reviewed this a lot yesterday, and I'm sorry if this was really quick. I'll be here for 2 more minutes. Did everyone have a good time? A little bit extra review? Did this help with some concepts? I just decided to experiment and do this and log on and say, hey, I'll be online for about 30, 40 minutes. Did you guys like this? Was this helpful? We'll see if people say yes or no. People are like, no, this was a horrible idea. I'm debating on if this helps people, we should do this a lot more. There you go. Awesome. Well, I hope, we always want your guys' responses on this. If you're finding this helpful, we're trying to do it more. Very helpful, I like that. Thank you guys so much. Ultra low latency seems to be on like a 6 or 7 delay right now. If we feel comfortable, do the practice exam, how's our chances? If you feel the practice exam is really good, I would say you'd make at least an 80 on this exam. Now I can't say, I don't know if you'll make an 80. You might make a 90, you might make a 100, you might make a 70, but I would say people who feel comfortable with the practice exam are probably on track to make a B on average with a standard deviation of 6. 85 with a standard deviation of 6. There's variation, but people who feel comfortable are going to do better than those who don't feel comfortable. Be watching those videos. I won't be able to respond to as many emails for the test because I'm going to go teach, and I might be back around 4:10, so stay tuned. If you want to come in and ask more questions, we can do more, but that's got it. Thank you all very much. We'll end with crab rave. So bye everybody, have a great evening. I'll be back, see you later tonight.